Now let us study the multinomial theorem, which is basically an extension, or we may say the generalization of the binomial theorem. Now just to recap about the binomial theorem, we know that given any binomial, say x1 plus x2 raised to the power n, now this expansion can be done with the help of binomial theorem. But what if we have more than two terms inside the bracket and we have to expand that to certain degree n? So this is what is given by the multinomial theorem, and let us see how to expand that particular expansion. So multinomial theorem is, suppose we have x1 plus x2 plus x3 plus so on up to say xr whole raised to n. So basically there are r variables inside the bracket and which are raised to the degree n. Now this is given by, now there is a big summation here, that is because we have to consider the sum taken for a different particular types of the terms. Now the first term is n factorial divided by a1 factorial, a2 factorial, a3 factorial and so on up to ar factorial, where these numbers, that is a1, a2, a3 up to ar, are nothing but the indices of the respective variables, that is x1 raised to a1, x2 raised to a2, x3 raised to a3 and so on up to xr raised to ar, and with the restriction that sum of all these indices must together be equal to n. So that means the summation is done under restriction that the sum of a1 plus a2 plus a3 plus so on up to ar should be equal to n. So this is a formula to expand x1 plus x2 plus x3 and so on raised to n. Now one of the very important application of this theorem is to find out the number of integral solutions for the equation shown as here, that is x1 plus x2 plus x3 plus so on plus xr is equal to say n, where we have certain restriction, that is each variable xi lies between some interval, that is say ai to bi. So if that is the case, then the number of integer solutions for this equation is same as the coefficient of x raised to n term in the product as shown here, that is the product of, if you observe here, the first bracket involves various powers of x which are actually the restrictions on first variable, because we know that x1 varies from a1 to b1. So therefore starting with a1 we have various powers of x which go up to b1. Now if we consider the second bracket, there we will see the powers of a2, a2 plus 1, a2 plus 2 and so on up to b2, which is nothing but the set of all the possible values which x2 can take, because here it's given that x2 lies between a2 and b2. So whichever are the numbers given to us in the problem. So in that way we continue up to rth bracket, because each of the r variables will have their own permitted intervals. So this is how we have to calculate the integer solutions for the equation, and there can be multiple cases based on what are these intervals. So as a special case, let's see the question where we are asked to find the number of non-negative integer solutions of this particular equation, x1 plus x2 plus x3 plus so on plus xr is equal to n. Now non-negative integer solution means that each of the value of these variables must be non-negative. That means it can be 0 or it can be a positive integer, that is a natural number. So here we say that 0 is less than or equal to xi, and obviously we know that that would range up to n because that is what is the maximum sum that we want. So any variable cannot cross n. Now to find this, what do we do is, as we have seen earlier, the number of integer solutions of this particular equation is same as the coefficient of x raised to n in the product of, now if you see, we have to write the first bracket for the first variable x1, and since it ranges from 0 to n, so therefore we will start writing the various powers of x starting with x raised to 0 plus x raised to 1 plus x square plus so on up to x raised to n. Alright, this is for the first variable, that is x1. Now for the next variable x2, we have once again the same set of terms in the second bracket, and so on we will have r variables. So that means this particular bracket will multiply itself r times. So therefore we have this bracket raised to r. So we have to find the coefficient of x raised to n in this particular term. So therefore let us see what does that come to. So this is same as the coefficient of x raised to n in. Now x raised to 0 is nothing but 1. Then we have x, then x square and so on. Now if you observe, even if we continue beyond the terms which are having the degree of x more than n, still it will not cause a problem to find the coefficient of x raised to n, because the higher terms or the terms which are degrees higher than n will never come into the multiplication to give us the term in x raised to n. So therefore, even if we include the terms after x raised to n for infinity, still that will not have any difference in the coefficient of x raised to n. So therefore, moving ahead, this is equal to, now if you observe, whatever bracket we have got, that is nothing but a geometric progression with the first term as 1 and the common ratio as x. And we also know that this is going on for infinity, that is, this is a kind of infinite geometric series, and we know that this is a standard expansion of 1 upon 1 minus x. So we have 1 upon 1 minus x whole raised to r. So therefore this is nothing but coefficient of x raised to n in. Rewriting the negative index, we have 1 minus x raised to minus r. So that is the coefficient of x raised to n in. Now here we expand 1 minus x raised to minus r using the binomial theorem, because now we have binomial here. So first term is 1 plus we have minus r into minus x, then we have minus r into minus r minus 1 whole upon 2 factorial into minus x the whole square plus so on. Basically you will see that if the power of x is 1, then here we have r. If we have, or if we consider the power of x as 2, then you will see that this particular term is nothing but r plus 1 c2, taking the minus signs outside. So therefore in general, finally when we solve and reach to the term which is having x raised to n in that, we will see that the coefficient of x raised to n turns out to be n plus r minus 1 c n. And as we know the property of combination, that is, this is same as n plus r minus 1 c r minus 1, because we know that both of the lower numbers here add up to n plus r minus 1. So basically the sums involving these types of questions, that is to find the number of non-negative integer solutions or maybe some other integer solutions, we have to basically write this particular product as shown here, and then based on the expansion and collecting the required terms, we can get the coefficient of x raised to n.